Yesterday we began this process of looking at relative motion, at least relative motion in two dimensions. We began the process of looking at relative motion long before Physics 20. In grade 6, you learned to add positives and negatives together, which really, if you translated that to a physics example, was relative motion in one dimension. The example that we gave you yesterday was that if you had an airplane traveling at 800 kilometers per hour, and you threw a baseball at 100 kilometers per hour, either to the front or the back of the airplane, then the velocity of the baseball relative to the ground, or the relative velocity of the ball, would be either 900 or 700, depending upon which way you threw it. How did we figure that out? Well, we added vectors together. We added 800 plus 100, or 800 plus negative 100. When we add those vectors together, we get the relative velocity, the velocity relative to the ground. Now, when we're doing that in two dimensions, we got to add vectors together too. It's no different. We have to always add vectors together to get relative velocity. But when we're adding them together in two dimensions, the math is a little bit harder than when we're adding them in one dimension. But we've taken a look at that over the last week or two, adding vectors together in two dimensions. When we do that, the goal, if you remember, is always to get a right-angled triangle. So that's what we try to do, get a right-angled triangle. A vector diagram drawn as a right-angled triangle. And then once we have that, we can find the resultant, which will be the relative velocity, by doing the Pythagorean theorem and the inverse tan function, just like we did on the quiz, except that wasn't in the context of velocity. That was in the context of displacement. Now, when we're given one of these problems, it's not going to be worded quite as simply as the problems that we've done to this point. The mathematics is going to be probably easier, but the wording is going to be a little bit harder. A question might say something like, the captain of a ship aims his ship directly west across the river, but there's a river current flowing to the south. Which way does the ship end up going? That doesn't sound at all like one of the problems that we've done over the last week or so, but it is. In the end, we add those two vectors together, the direction that he heads and the direction of the river current. We get the resultant vector, which is the velocity of the ship relative to the ground. In other words, which way the ship actually goes. In order to interpret the wording of these questions, we want to separate our vectors into two categories. And these are kind of loosely defined categories, categories that I've set up just because I think it makes it easier to do this. We call them solid line vectors and dotted line vectors. Solid line vectors are vectors that will contribute to the actual velocity. They'll contribute to where you actually go. They're not where you go. They contribute to where you go. They help get you where you go. For instance, if you're swimming across a river and there's a river current of 2 meters per second to the south, you're not actually going to the south. Right? You're swimming across it and the river current is taking you downstream a bit, but you're not actually going there. But that contributes to where you go. If you're aiming directly west across the river as you swim across the river, you're not actually going west because the river current is carrying you south. But where you aim contributes to where you go. So what contributes to where you're going, we're going to draw that in our vector diagram as a solid line vector. Whereas our dotted line vector is going to be where you're going. Not what contributes to where you're going, but where you're going. In the case of you swimming across the river, what contributes to where you go is where you aim and the river current. Where you go is some sort of combination of the river current and where you aim. In other words, the resultant vector, the total, the sum of where you aim and what the river current is. Remember we said a few minutes ago in the example up here, where the baseball goes is the sum of the velocity of the airplane and the velocity of the ball. We add those two vectors together. They'd be solid line vectors because they both contribute to where the baseball goes. Where the baseball goes at 7 or 900 kilometers per hour would be my resultant velocity. That would be my dotted line vector. Same deal here, except we're dealing with 2 dimensions instead of 1 dimension, that's all. All right, so what would be some examples of solid line vectors? What would be some examples of things that would contribute to where something goes? Depends on the context, I suppose. But where we aim, in general, contributes to where we go, or where we head, in general, contributes to where we go. So whether we're in an airplane and we're heading to the north, or whether we're in our car and we're heading to the north, or a boat and we're heading to the north, or we're just walking and we're heading or aiming to the north, we're going to make that a solid line vector, because that's not necessarily where I go. That's what contributes to where I go. We'll skip over the second one for a second. We'll come back to that. Wind speed and river current. If I'm flying to Edmonton, but there's a wind current that goes to the east at 40 kilometers per hour, I might end up east of Edmonton. But I'm not going to end up straight east of Edmonton, right? If the wind current is to the east, I'm not going to move to the east. I'm going to move kind of northeast somewhere. But in the end, the wind contributes to where I go. It's not where I go, but it's what contributes to where I go. Same deal with the river current. Swimming across the river to the west, river current flows to the south. You're not going south, but the river current to the south contributes to where you actually end up going. Finally, the airspeed. What do we mean by that? Well, the airspeed of an airplane is the speed that an airplane can travel without wind. So in still air, in calm air, how fast it can travel in calm air. I don't think WestJet does this, but Air Canada, if you've ever flown Air Canada and you have a look at the magazine in the seat pocket in front of you, at the back of the magazine, they always have pictures and information about each of the different kinds of airplanes that they fly. I don't know why I find that kind of interesting sometimes, but I look at that. I always read that and look at all these different airplanes and look at the capacity of the airplanes and the fuel capacity and the airspeed of the airplanes. When they talk about the airspeed of a 737 jet being 800 kilometers per hour, that means if there's no wind, that's how fast it can go, 800 kilometers per hour. Okay, another one might be 900 kilometers per hour. If there's no wind, it can go 900 kilometers per hour. Well, that's not how fast it actually goes. That's what contributes to where it actually goes, right? If it can go 800 kilometers per hour with no wind, well, then that combined with the wind speed gives me where I'm actually going. So that would be a solid line vector as well. The speed in still air contributes to where I go. It's not necessarily where I go, but it contributes to where I go. Versus my dotted line vectors, well, where do I actually go? Where do I actually go? Well, that's not a solid line vector because that doesn't contribute to where I actually go. Where I actually go is where I actually go. It's not contributing to anything. I'm heading towards Edmonton. There's a wind speed to the east. I actually end up going kind of northeast. Solid line vector to the north, solid line vector to the east, dotted line vector to the northeast-ish, telling me where I should go. Also, where you want to go. I may want to go to Edmonton for some reason, but there's a wind speed that's carrying me off course. Where I want to go would be a solid line vector, a dotted line vector as well. We'll assume that if you want to go north, then you'll end up going north. And finally, another one, the ground velocity, or the velocity relative to the ground, would make a dotted line vector as well. It's a resultant vector as well, so therefore a dotted line. So let's do an example here. This question says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. However, there's a wind of 50 kilometers per hour to the east blowing. Where does the plane actually end up going? Well, remember, not so much the specific examples of solid and dotted line vectors, but fundamentally, what is a solid line vector? What is a dotted line vector? Solid line, remember, contributes to where we actually go. Dotted line vectors are where I actually go. So let's look at these vectors again that's given to me in this example. The pilot of a plane heads directly north. He or she aims to the north. Does that contribute to where I go, or is that where I actually end up going? It contributes. So is that a solid or a dotted line vector? It's a solid line vector. Good. So let's draw this 200 kilometers per hour to the north as a solid line vector. We're aiming to the north. Notice these are kilometers per hour, not meters per second, not meters. We're not measuring displacement vectors anymore like we were up until today. We're measuring velocity vectors now. We could measure momentum vectors or force vectors, quantities that we've never seen before. Vector diagrams aren't just for displacement, they're for any vector. So we get 200 kilometers per hour to the north, and then we got a 50 kilometer per hour wind to the east. Does the wind contribute to where I go, or is the wind where I go? It contributes, right? It contributes. So it's going to be 50 kilometers per hour to the east. Now I got two options. I can draw it right here. That's drawn front to back, right? Or I could draw it right here. The first option is probably the best one, but it doesn't really matter, as long as it's drawn front to back. My resultant vector, my dotted line vector, where I actually go, is the hypotenuse of those two sides of the triangle. So you want to find that value? (200 squared plus 50 squared) gives me, I think it's 2.1 times 10 to the 2, about 210, 211. 206.15, and technically we should start rounding this to significant figures, so we're going to say 2.1 times 10 to the 2 kilometers per hour. So the pilot is aiming at 200, but the pilot ends up going a little bit faster. Does that ever happen? You ever been in an airplane when you're scheduled to arrive at a certain time, but you left the gate a little bit late, so you think you're going to be late arriving, and the pilot comes on and says, we got a tailwind, we're going to make up a little bit of time here? You ever heard the pilot say that? What does that mean, a tailwind, we're going to make up a little bit of time? What he or she is saying is what, Nathan? Yeah, so if you were aiming at 200 kilometers per hour, which would be a pretty slow airplane, right? But commercial airplane at least. Maybe you end up going at 210 or 215 or 220 because there's a wind that's helping you. Okay? Just because the wind isn't going exactly as a tailwind, like in this question, doesn't mean that it can't speed you up. It speeds you up a little bit here, marginally, but still measurably. Okay, theta, we got to find the direction at which the plane actually ends up going. It's going to be the inverse tan function of opposite over adjacent, 50 over 200. It's going to be a fairly small angle. I'm going to say 20 degrees. 14 degrees. And what would that be? 14 degrees what of what? Sam? It would be east of north. Good. Had I drawn it the other way with my x-axis first and my y-axis second, it would have been 76 degrees north of west. North of east, I should say. Yeah. Make sense? Listen, some of you might take physics because, you took it in Science 10 and you did pretty good in it. Some of you might take it because you like it, although probably not. Some of you might take physics because, you need it to go into the program, you want to go into university. Some of you may just be taking it just because. You want to keep your options open. There's lots of careers where you'll use physics, right? You want to be a physics teacher, you want to be an engineer, you want to be a geophysicist, you're going to use physics lots. But you can imagine here maybe, just maybe, if you wanted to be a pilot, how maybe might be useful to know something about vectors if you want to be a pilot. Okay? If you want to go to Edmonton, you need to know if there's a wind blowing to the east, then maybe your heading is not going to be straight to the north, right? Maybe your heading has to be somewhere else, right? You need to know something about vectors. So it's not just engineering or geophysics and physics teacher or whatever. It's you want to be a pilot of a plane or a captain of a ship, you got to know something about vectors as well. Yesterday I gave you a worksheet. You know what, let's do one more example actually before we set you free on the worksheet here, okay? One more example. And then we'll give you some time to work on the worksheet. This one is the captain of a ship. All right, no big deal. Pilot of a plane, the captain of a ship, aims her ship east, but there's a current that puts the ship off course. We should have a direction of that, a current of 10 kilometers per hour to the south. It puts the ship off course. Where does the ship actually go? Well, let's draw it out. She aims her ship at 20 kilometers per hour to the east, yes. Is that where she actually goes? No, it's not. Julia, what is it? It's contributing to where she goes, right? So that's going to be a solid or dotted. Solid. 20 kilometers per hour to the east is a solid line. Now we've got a 10 kilometers per hour to the south. That's a river current. Victoria, is that where she goes, or does that contribute to where she goes, the river current? It contributes to where she goes. Yeah, it was you. Yeah, let's look at it. It's confusing when there's two of you right beside each other. It contributes to where she goes, so that's a solid line vector as well. Now, where she actually goes is this dotted line, represented by R and theta. R is the square root of 20 squared plus 10 squared. Square root of 500, I'm going to say 22-ish, 22. And I'm going to find theta, saying the inverse tan function of opposite over adjacent, 10 over 20. I don't know, I'm going to say 30-ish degrees. What does it work out to be? Nathan, you got that? 26.56, so we're going to say 27 degrees. So we're going to say 27 degrees what of what? The only axis that's in this picture is the east axis, and we're going south from the east. So it's going to be south of east. How many people have the driver's license here? Just about everyone. Have you guys ever noticed, you're driving down the highway, maybe towards Calgary, there's a Chinook blowing. Like, sometimes those Chinooks blow like crazy, like up to 100 kilometers per hour. We've had Chinooks here that are actually hurricane force winds. They're not classed as hurricanes because of how they're produced, right? But they're actually hurricane force winds. So it's crazy driving in that sometimes. Usually it's blowing to the east. You ever notice when you're driving and there's that crazy strong wind to the east, sometimes you've got your steering wheel, just to go straight on the highway, you got your steering wheel turned like that, right? You're aiming over there towards Bragg Creek somewhere so that you can end up going towards Calgary, because where you aim and the wind contribute to where you actually end up going, right? Solid line and solid line contribute to where you actually end up going, the dotted line. Does that make sense? Yeah.
Not only was it really windy, but it would like get really windy, but then it would stop.
Oh. So gusting a lot, yeah.
Yeah, but like because like the person taking the test like was like, oh, you were all over the road, fail.
Was that right?
And it was just because she was like adjusting for the wind.
Yeah.
The wind would stop and she'd be like.
Yeah, that's hard sometimes. It is, yeah, for sure. Yes, yeah, it was very windy, yeah. It's funny though. You've never learned about this relative motion, these adding vectors together, right? But somehow, if you were driving to Calgary and there's a strong wind to the east, somehow you still knew to aim to turn the steering wheel that way, right? To get you going straight up, right? So there is an intuitive grasp of this before we actually do the mathematical aspect of it, right? You guys good there? Okay, let's take a look at that worksheet now then. Let's see what you can do with the first 3 questions on the first page of that worksheet, okay? Let's take a look at another example, which is pretty much the same. They just ask it, or I just ask it in a slightly different way. This says the pilot of an airplane wants to go, no, that's not the one. This is the one. The airspeed of an airplane is 800 kilometers per hour. That's how fast it can travel if there's no wind present, right? That's the statistic that it gives in the back of that magazine, that in-flight magazine in the back of the seat pocket in front of you when you're sitting in the airplane. How fast it can go without a wind. The pilot of the plane aims his plane west, but there's a 75 kilometer per hour wind to the south, sends the plane off course. What's the ground velocity of the plane? What's the velocity of the plane relative to the ground? In other words, where does it actually go? Same question as we've just asked twice already, but just looks a little bit different. We aim to the west. We're aiming at 800 kilometers per hour to the west. There's a wind of 75 kilometers per hour to the south. Those are both solid line vectors because those both contribute to where this plane actually goes. The dotted line vector is the ground velocity, the velocity relative to the ground. We're going to find that by saying the square root of 800 squared plus 75 squared. And we're going to find theta, the angle, by saying the inverse tan function of 75 over 800. And when we get that angle, whatever it ends up being, it's going to be measured from the west. So we're going to say that it's whatever degrees south of west. The only axis I have here is the west axis. The angle is measured from that west axis, and it's coming to the south of west. All right? Now you can take a look at 4 and 5 on the back of the page. 5, I'm going to warn you right now, is going to give you a little bit of trouble. Okay, it's a challenging question. 4, pretty much exactly what we've just done here. Okay, see what you can do with 4, and especially number 5, and then we'll go over in a few moments question number 5 here, okay?